I'm Sarah Vaughan, and I'm your host for this afternoon, and I'm a creator of Brands with Purpose. And we've got a really fascinating session this afternoon looking at the future of tech for the 22nd century. Now, that's a very interesting thing to consider, given that we've got IPCC and various other organizations saying that we've got a climate catastrophe heading towards this in only 11 years. So I'm very interested to hear what our amazing panel of speakers have got to say to us on that matter. So first up is going to be Sims. Welcome, Sims. Sims is from DeepMind, and she's going to be talking to us about the future of energy.
All right. Hi, everyone. Ooh, it's loud. Thank you very much for being with us today. Climate is one of the most definitive issues of our time, and at DeepMind, we are working on 2 projects that have proved that you can actually apply machine learning to help solve some of the challenges that contribute to climate change. So there are lots of ways and lots of areas where machine learning can be applied to climate. Now, this slide is on mitigation strategies. Many of you will be aware there's also adaptation. But within all of these areas, and there are more, our team focuses specifically within energy. Now, even within this sector, there are lots of different places where we could apply machine learning. There's generation, there's consumption, there's scheduling, there's dispatch, there's fusion. So you can see there's a huge opportunity here. And our team has focused on consumption and generation. Now, on the consumption side of things, we're working on increasing the efficiency of existing systems because, of course, we can't just wipe out all of our infrastructure and start over immediately. We need to be optimizing our current processes while we're building new solutions. On the generation side of things, we're working on increasing the value of renewable energy, specifically wind power. And we've done both of these by piloting with Google. So first in the data centers for the Industrial Controls Project, and next in the Google contracted wind farms for our renewable energy, or our wind power project. First, we're going to deep dive into the consumption side of things and take a look at what it is meant to increase the efficiency of industrial systems. Now, if we think about an industrial system, let's simplify it just for the sake of easy maths, and say, assume a system has 10 pieces of equipment. Now, many of you know that complex industrial systems have many more than 10 pieces of equipment. But imagine on each of those 10 pieces of equipment, there are 10 set points, or 10 things you can change to adjust for energy efficiency in a system. Now, that's already 10 to the 10, or 10 billion possible configurations of that plant. Now, I don't know if that sounds overwhelming to anyone else, but that's a lot of options if I'm a facility manager and I'm imagining having to go through all of those to find the most energy efficient setups in a system. Those are just so many permutations. But one of the things that these kinds of systems have, even though they're immensely complex, they're also a very data-rich environment. So all of a sudden, we're starting to kind of see the perfect test bed for AI. We've got a data-rich environment, we've got measurable rewards, so energy efficiency, and we've got specific actions, or what we call in AI an action space, specific things we can control to adjust for efficiency. Now, on top of all of this, why did we start with data centers? Data centers consume 3% of the world's energy, and they're also, again, data-rich environments. But the cooling systems are particularly interesting because if you think about industrial processes, you kind of have to drill down into one. And so we were like, why don't we start with HVAC systems? Now, for data centers, cooling is incredibly important because many of you imagine how hot your laptop gets when you are streaming videos or watching cat and dog videos on YouTube. Now, imagine that your laptop is the size of a small village. I mean, how hot that would get. There are literally chillers the size of buses in these data centers. So being able to control the cooling is just an immense project. So what did our team actually do to do this? Well, we took over 2,500 data streams from across Google data centers and an action space, or things we could control, about 20 different actions. We built an AI system that then took every 5 minutes a snapshot of the Google data center, so we understood the state of the system every 5 minutes. We then cleaned that data and got it prepared to be fed into the models. Our models then generated a set of recommendations and an hourly forecast on energy efficiency. So it said, what set points do we change in what pieces of equipment and by how much in order to increase energy efficiency for the next hour? Now, it also satisfied some very rigorous safety constraints because obviously we want to make sure we're protecting the equipment as well as the safety of the entire system. We then gave those recommendations to a human operator, so the data center managers and facility managers, to manually implement those recommendations every hour on the hour. And this is what it looked like on the average day at a Google data center. You can see where we turn the ML system on, there's an immense drop in the amount of energy we're using, and when we turn it back on, that rises again. For those of you who want to know what that delta actually is, it is 40%. Now, this is an amazing amount of savings. We were incredibly excited by this. And not only the increased energy efficiency we were able to achieve with our ML system, but also the fact that the AI was able to teach us new information. This is a quote from Dan Funfinger, who's one of the Google data center operators that worked with us very, very closely with our AI system. And he notes here, I won't read the quote because you all can do that, but he notes here that the AI system was actually able to not only deliver savings, but teach us new information about how to control the system and to take advantage of what it had learned in the data. But he did have some feedback for us. He said, okay, well, if you guys, before you came in, these systems are usually run by pre-programmed rules and heuristics. Like, we get to exist in a very supervisory capacity and use our domain experience to make sure the system's running safely. But with this AI optimization, it's great. We have 40% energy savings, but I'm having to go in and manually change every hour on the hour all of these set points. That is a lot of work. So they asked if we could build a direct control system. And we said, yeah, okay, we think we can do that. So if you note, the first part of the system looks exactly the same. We took a snapshot of the data center from all of those sensors. Every 5 minutes, we cleaned the data, we fed it into the models. The models, again, generated a set of recommendations on what set points to change and by how much based on improving the energy efficiency over the next hour. But it's the next part that changes, because although we continued to go through the safety constraints of the cloud-based infrastructure, we also went through safety constraints of the physical infrastructure before directly implementing those changes in the data center system. Now, this is huge because from our knowledge, this is the first time we've seen an industrial facility of this size and having the cooling directly controlled by AI. And because of that, we implemented no less than 8 new safety mechanisms in order to ensure the system operated exactly as we intended it to. Now, for the sake of time, I don't have time to go through each one of these individually, but if you're curious, please talk to me after. I'm happy to geek out with you over them later. So the Safety First system delivered 30% energy savings, and that number is growing. Now, some of you might say, oh, hey, 40% with the human implementations and 30% with direct control. Like, what's going on with that 10%? Well, you have to remember that we constrain the system with additional safety requirements, and this number is growing. These are our initial findings, but the more we allow the system to explore and the more time passes and we're able to loosen those safety constraints, the higher this number will get. In fact, this is my favorite graph because you can actually see the blue line is the training data we've had, and then you can see the amount of energy we actually have used decrease. In other words, AI is getting better over time. With the more data we have, the better our system gets and the more it learns. So now hopping over to the generation side. So that was how we were improving the efficiency of existing systems using an AI system in an industrial setting. Now we'll pop over to the generation side and see, I'll talk a little bit about how we have increased the value of renewable energy, specifically wind power. Now, one of the problems for wind power is the intermittency. Those of you who are familiar with renewables will know that you can't schedule renewable energy the way you can fossil fuels because we're simply sometimes, in this case, at the mercy of the wind. Sometimes the wind blows and you have power, other times it doesn't, and you're stuck. And so, whereas with fossil fuels, obviously they can deliver a set amount of power at a set time. They're just a bit more reliable. So our solution was, what if that wasn't the case? What if we could use AI for predicting energy, wind energy output, and then use those predictions to schedule and make more reliable commitments to the grid? This is what our system actually looked like. We took the inputs of global numerical weather forecasts as well as historical power production data from the wind farms. We then fed that into a neural net, and I need to mention, we're actually controlling 700 megawatts, applying this to 700 megawatts of wind power, so that's enough to power a small city. So this is a small to medium-sized city. This is a massive amount of wind power that we're applying this system to. And what the output from the neural net is for all of that power is future wind power output, so the predictions that would say, okay, this is how much power we think that you're gonna have at each hour during the day. And we're doing this about a day or so in advance. So this is important because then what we can do is we can make commitments to the grid in advance. And there is a premium for that dependability and that reliability. And you can see here, the blue line are our predictions, so what we were giving about a day or two in advance. And then the gray lines are the ground truth. So you can see that they follow each other pretty closely. And what I also love about this graph is that you can see the immense volatility of the wind. In just a matter of hours in some of these spikes, you can see we go from producing 0 megawatts of wind energy all the way up to 200, which is a massive amount of power. And so, the truth of the matter is we're not ever going to be able to completely eliminate the variability of wind. But with an AI system, we may be able to make it a bit more predictable and remove a bit of the complexity. And we have indeed seen that we were able to increase the value of renewable energy by about 20%. And this is compared to the baseline of not being able to make day-ahead commitments to the grid. Now, 20%, that's really exciting for us. And if we're able to increase the economic value of wind power and make it more competitive with fossil fuels on the energy markets, what we're hoping is that we can also speed the adoption of renewable energy and help to decarbonize the grid. So since this track is about the future of technology, and this is a technology that we have today that is immensely impactful for the future, I just want you to put on your thinking hats for a minute and think about that industrial controls project and the increasing the efficiency of industrial systems. Now, I mentioned that they're right now consuming 54% of global energy. Imagine if we could achieve that 30% savings on 54% of global energy and what that would mean for carbon emissions reduction. The same thing with renewables. If we were able to adopt this technology on more wind farms worldwide, what that would mean for making wind power globally more competitive with fossil fuels and hopefully decarbonizing grids worldwide. And like I mentioned earlier, AI gets better over time, so I think we have a lot to look forward to. Thank you very much.
Thank you very much, Sims. I've just got a question, a burning question for you.
Great.
Which is, what is the biggest challenge in applying machine learning in the real world?
That is a fantastic question. Applying machine learning in the real world means that you're working with real-world data. And for those of you in this industry, you know that real-world data is very, very messy. So I would say data quality is our biggest challenge. We spend 80% of our time cleaning data. And, if we could, we're already working with, policymakers. There's some really interesting work going on in the UK, actually, with the Energy Data Task Force to work on data standards to improve the quality of data in this industry. We think that work is fantastic, and we're really looking forward to seeing those recommendations when it comes out because, data quality is definitely our biggest challenge.
Thank you very much, Sim.
Thank you.
Great. And now it's my pleasure to welcome Tom Wilson from Graphcore to the stage. And Tom's going to talk to us about autonomous vehicles and intelligent machines. Thank you, Tom.
Thank you. So I'm going to have more of a transportation focus here now in ways that AI can help us with that. Now, before I start talking about autonomous vehicles and intelligent machines, I'd like to talk a little bit, maybe the first slide. Oh, sorry, that's up to me. There's no AI running this thing. I don't know what's going on here. So I'd like to talk a little bit about the image on the right-hand side of that screen. So that's an output from our software tools called Popular. And that is basically consumed by our Intelligence Processing Unit, or IPU. And while this is in detail comprised of millions of parameters and relationships and tens of thousands of programming tasks or programs, it's kind of misleading to describe this as simply a program. We actually refer to this more as a knowledge model. Now, Graphcore is implementing hardware solutions with the IPU and software tools to basically provide a brain for computers to process information more in a way that a human does. And my role at Graphcore is to work with the automotive industry and this new processing approach to enable autonomous vehicles. So we're basically teaching machines how to drive, which kind of leads me to a little bit of a personal story, just to give you some personal background. Before I got into AI and into automotive and into semiconductor, even before I got my PhD in plant physiology of all things, I don't know how I came from there, but anyway, before that, I was a driving instructor. So in my early 20s, for about 3 years or so, I taught humans how to drive. And I think it kind of gives me an interesting perspective on what it takes to teach a machine how to drive. And it was kind of a crazy job. But what was interesting was this learning process that the student would go through. When they first got into the car, the driving tasks were sort of an assemblage of disconnected tasks that they needed to put some conscious attention to, whether shifting gears or managing the clutch versus the gas pedal, or steering, being aware of where their hands were on the steering wheel when they turned a corner, signaling, looking at their mirrors. But at some point in time, magic happened. And they would transition from the point where this was just an assemblage of separate tasks to an integrated skill, and they became drivers. When that happened, how much time that took was very dependent on the students, and it was very age dependent, actually. But regardless, over some amount of time, some amount of learning and experience, they became drivers. So when we look at the same process with machines, it's a very different sort of task. And before we get into more of the task of teaching machines how to drive, it's important to sort of associate ourselves with some lingo. So this is a standard way of looking at the different levels of autonomy, beginning from about level 0 up to level 5, where it's fully autonomous driving. So from level 0 to about level 2, it's really more about driver assist functions. So emergency braking, lane keep assist is where the car helps keep you in the lane. And actually, these are all things that I used to do as a driving instructor to keep the student in the lane, and I had a brake so I could hit the brake if there were problems. Now the car is taking over those kinds of driver assist functions for you. It's level 4 and level 5 where that magic now needs to happen, and the machine needs to begin to take over. Especially level 5, where this is really car as a service, or for robotaxi, where there may not even be controls for a human driver to take over from. So how close are we to that magic happening? How close are we to that level 5? Well, it's actually taking a little bit longer than we thought. So we're probably about a couple years away from where we thought we would be a couple years ago. And a lot of that has to do with the fact that the industry's been in a state of where we just don't know what we don't know. The focus largely has been just on perception, on teaching the machines in the vehicle to actually build a three-dimensional map of what's around them. And it's only now that we're beginning to get into more sophisticated tasks like reinforcement learning and predictive algorithms, so that the machine can begin to anticipate what's going to happen around them. So just to go into a little bit more detail around what we don't know about, is one thing we do know is that there will be an ongoing need for legacy processing. So we'll need conventional processing to continue to interface with the vehicle, to run low-level application processing. But on the AI processing front, up to now it's been mostly about acceleration, and mostly accelerating perception tasks. We need now to move away from just accelerating perception processing to really beginning to develop the machine that learns and anticipates its environment. So really moving towards a learning machine. And we don't know what we don't know in terms of what those final algorithms will look like and the processing requirements that they're going to require. As far as the sensors go, again, there's lots that we don't know about the final mix of sensors. What we do know is it continues to increase. There's an increasing amount of radar and more raw data with radar, increasing number and resolution of cameras, 8 megapixel, 12 megapixel cameras surrounding the vehicle. And in the case of robotaxi and L5 particularly, some sort of scanning LiDAR, horrendously expensive, tens of thousands of dollars, scanning LiDAR on top of the vehicle, spinning around, constructing a high-resolution point cloud to help us map around the vehicle. And the whole purpose of all of these sensors is to build a very detailed three-dimensional map, an environmental model, it's called, around the vehicle. And I find this a very interesting differentiator between the machine student, as it were, and the human driver. Because when a human driver jumps in the car, they've got one camera. It's a forward-facing binocular camera that's supplemented by 3 mirrors, really small mirrors with big blind spots, and some ears to kind of listen for issues, and the ability to rotate that camera 90 degrees one way or the other using this really cool feature called peripheral vision to check the blind spots. And that's it. Because the human driver is not concerned about building an elaborate, extensive, exhaustive three-dimensional map. They're trying to build an extended kind of situational awareness, which is different than a detailed 3D map. So situational awareness in the autonomous vehicle translates into this detailed 3D map, which is very different than situational awareness. The student human needs to make decisions based on very imprecise, sparse data. So situational awareness then means learning from experience, and where that experience happens to be very sparse and imprecise data. So we really need a machine that can learn from experience. We're already beginning to do that with algorithms, but really build a machine that is good at that, that's actually designed from the ground up to do that. So how difficult is it to build an intelligent machine? Well, it's actually pretty difficult, and people have been trying to do it since the 40s. But just in the last 5 years, we've been seeing real advances. One of the things helping us is that now we have increasing amounts of data, the right kind of data, and the more data you have, the better the machine learns. We also have better compute infrastructures to allow us to actually run this amount of massive amounts of data to actually learn from that experience. But the problem is that you really need the right sort of compute platform, a new kind of compute platform for what we would call Compute 2.0. Because the problem is that processors really are not getting any faster. Up until about 2008 or so, we were on a really nice ride where as we went down in process geometry and our transistors got smaller and smaller, we could run our processors faster and faster and for free. There's no increase in power. But all of a sudden in about 2008 that changed and it began to flatten out. We can't run faster without incurring big power costs. Since then, the industry has played with different kinds of parallel processing techniques, but what is really required is an entirely new way to approach the problem. And it means that sometimes it's not just evolutionary, it's a real jump. So if you, for example, if you look at propeller-driven airplanes, it doesn't matter how much horsepower you put in that engine or how aerodynamic you make the airplane, you can polish it all you want, there's only so fast you can go. You need to make a jump, you need an entirely different kind of technology to go faster and to break the sound barrier and beyond. And likewise, with the processor architecture, Graphcore began with a clean sheet of paper and looked at what was required for machine intelligence processing. If you were to design this from scratch, what would that look like? Well, to answer that question, we have to look a little bit more closely at what machine intelligence processing is all about. Well, what we're trying to do is learn from data. So we want to be able to extract parameters, features, find the relationships, the strengths of those relationships amongst those parameters and extract that from data. We do that by constructing graphs in high-level machine learning tools, and those graphs then extract the parameters from training data. We're able to construct knowledge models like this. Now, these knowledge models are naturally represented as hyperdimensional, high-dimensional graphs of tensors. When these high-dimensional graphs are saved into computer memory, they're really spread out in a very sparse manner across memory. So what we need is a compute platform that's able to work with that kind of sparse data, massive memory bandwidth to support tens of thousands of processing tasks running in parallel, and the ability to scatter gather data from widely spaced areas in memory very rapidly and in parallel. And that is essentially what's been built with the intelligence processor unit. So it's a machine intelligence graph processor. This becomes even more important as we begin to move to more advanced algorithmic approaches like for reinforcement learning, where you're working with things like long-term, short-term memory models, or LSTM. They're even more sparsely populated within memory. They're even more complex. And conventional processor architectures have an even tougher time with them. So as we move towards reinforcement learning and machines that learn, this kind of processing architecture will enable us to really sort of innovate in ways we haven't been able to do before. So where does that take us back to the original question about, well, when will we have machines that actually have that transition and are able to drive the way that I would define driving? Well, if I put my driver instructor hat back on for a second, I would say it's pretty hard to tell because, like I said, it really varies from student to student. And this is a kind of student, a machine student, that I really don't have any experience with. But one thing I can say, one thing I do know, is that if it's able to learn from experience, if it's able to make that transition where it's able to anticipate, rather than react to what's going on around it, but anticipate what's going on and to some extent take control of the driving environment around it, then there's hope that it will be able to make that kind of transition. And with our processing architecture and our approach at Graphcore, we hope to make that happen. Thank you very much. So the question, I don't know if you heard, is when do we expect to see them actually driving around where we have to avoid them? Well, I get that asked a lot, and I've been thinking about it within the context, again, of driving instruction. And I remember students would sometimes, and I couldn't help it, they would just learn what they needed to learn to pass the test. And they would pay the cost to go out on lessons and just learn what they needed to learn to pass the driving test. But they weren't drivers. But they passed the driving test and they were legally allowed to go out on the road. I think the first wave of autonomous vehicles will basically pass the driving test. But I think it's going to take some time before they really sort of transition into what we might call drivers that can anticipate what's going on, and you can actually kind of sit back and relax.
Thank you very much, Tom.
Thank you.
Please give him a round of applause. So I'd now like to welcome our last speaker, Håvard. Here we go. And Håvard is the CEO of Spacemaker. He comes from Oslo, and Spacemaker helps architects and urban planners design buildings using AI. So please give him a round of applause.
Thank you. Is there a clicker here? Okay, this is the clicker. Okay, thank you. Okay. Here's the situation now. The world's population is about to explode. We're currently 7.7 billion people on the planet, and within only 30 years, we're going to hit 10 billion people. Now that's a faster growth than we've ever experienced before. And nearly all of those people, they will want to live inside cities. But our cities, they're nowhere near ready for this. Think about it. It's like most of us will experience more than 20% people in our cities, in our neighborhoods, in our lifetime. And here's the dilemma we're facing. There's no denying what's happening with the climate. The data is clear. The last 5-year stretch has been the warmest since the records began, and we're seeing these pictures of huge fires and historic storms and flooding. But here's something you probably don't know, is that more than 40% of carbon emissions comes from buildings. So buildings' demand for energy keeps growing on a global scale. So, and we know we need to reduce carbon emissions, but at the same time, we need to build more. And how do we tackle this? How do we make room for 2 billion more people in 30 years, without making our planet inhospitable? We have to find a way of designing better and smarter and more sustainable cities. And we need to do it now. And this means that urban planners and architects and real estate developers, they need to be more creative than ever before. They need to find new ways of meeting this growth, of building denser without reducing the quality of life. So they need to maximize the use of space while minimizing environmental impact. And that's a tall order, but there's a big problem, because the demands of new development are more complex than ever before, but our tools, they haven't kept up. And before I give you the full picture of how I got here, I want to take you a few years back in time. 5 years ago, when I was working as an architect myself, and I was asked to design my dream project. It was a few hundred apartments, family-friendly apartments in an urban center. And since the site was at an urban context, there was all of this complexity, all of these things that I needed to take into consideration. So I did what everybody does in that situation. I started consulting the experts. And all of these experts, they knew a tremendous amount about their own fields. I had meetings with structural engineers, or daylight calculation experts, or acoustic engineers, or geotechnics, or experts within accessibility or fire protection, even grocery store experts. And I think I counted more than 15 different experts who all kind of chimed in with advice on how to solve this. But the problem was, each and one of them, they could take weeks or even days or even weeks for them to just get back to me. And the daylight expert could advise me to put buildings in a way that would maximize daylight, but it would open up for more traffic noise. And then the acoustic engineer would say, here's how you should put the buildings, and then you'll solve the traffic noise, but then left the area for in shade for most of the day. So it just didn't add up. And what I needed something that could show me the advantages of each approach and also how they all added up, so that I could kind of determine the best overall design. Now, everywhere else I looked, I was in a situation where I kind of felt like this system is just outdated. And then I saw in other industries, and I saw that digitization was boosting productivity. And construction was kind of falling behind. It was slow-moving, and it was a slow-moving animal. It was actually the last living dinosaur. I think actually agriculture and hunting is even more digitized than construction. And I told my friend Anders, who's actually here today, because I was up against time. Time was running out, and I couldn't see the full picture here, and it was really frustrating for me. And we started discussing this, and for a fleeting moment, we thought that we could solve this by putting it into a spreadsheet. But we soon realized that we had to build something far more advanced. Now, luckily, Anders had a friend who was working with building those kind of technologies to help solve large organizational problems. And his name was Carl. And Carl thought we were crazy. He said, this is probably impossible. But if it is possible, it's going to change everything. So he wanted to give it a try. And our idea gave us a grant, which made it possible for us to build a prototype. And guess what? It worked. And gave us our first customer, and then another customer. And all of a sudden, we were working with the most creative and credentialed architectural firms in Scandinavia, and also some of the largest residential developers in the region, and some of them even global players. And I'm not going to give you a picture that this all happened overnight. It's been 3 years of hard work and building, but that far-fetched idea is now a real product and a company, and it's called Spacemaker. And Spacemaker is, we believe, the most advanced computational design platform using artificial intelligence to solve real-world construction projects across the globe. And for the first time in a public forum like this, I'm going to show you how it works. So first you input all the available data and design information related to your project. Things like where it is, the location, the kind of zoning, height restrictions, 2D and 3D versions of your current design, and then you start setting the criteria. What's most important for you? You might want to maximize daylight and minimize, traffic noise and maximize energy efficiency. And what happens is that the system starts processing through billions of possible design options and then returns the best possible layouts. So there's more than 80,000 computers starting to work in parallel in the cloud and then processing all of these design options that you can just click on. And each and one of them, you can open them in 3D, and to the side here, you can click on close to 100 different analyses that each and one of them would take hours or days or even weeks to get with just a click of a button. And what's even better is that what you see at the bottom here is that you can see all of the best options within one subject overlapping. So it's actually showing you where the best options is for each layout or for each design variable, but also how it all kind of comes together. So this is actually showing you the big picture in a way that simply wasn't possible before. Now, isn't this cool? I think so. And I should say that a big part of this success, these 3 years, has been a result from the people behind this. And we have a headquarter in Oslo, but we have people in Sweden, in Barcelona, here in UK, and also in Cambridge, Massachusetts, right next door to MIT. And MIT is really acknowledging the importance of computational tools in urban planning. There's a renowned professor called Ole de Weck who once said that the only thing harder than launching a rocket is building a city. And at Spacemaker, we believe that by using artificial intelligence, we can give architects powers that they never had before. And Anders, a guy called Anders Strenge, who's an architect and a co-founder of one of the most credentialed architectural firms in Scandinavia called Art Architects, he's using Spacemaker, and he's sharing here his experience of using it.
It's all about the right analysis from the start. It helped us to see if you combine the two good things here with the three good things over here, then you get a masterpiece.
And this is an important point, because Spacemaker exists to empower architects. So it means that they can answer briefs and with more confidence and in less time, but by allowing computers to do the computation, architects can be more creative. They can have more time to be creative. And as an architect myself, I have to say that this is the tool that I dreamt that I had, and I'm very excited to see that more and more architects and companies, not only in the Nordics but also outside Nordics, is using this. And it's been a phenomenal journey. And I'm also thrilled to share that we just raised $25 million from two venture capital firms, Atomico and Northzone, to help us realize this potential. So that means we're growing, we're hiring, and we're designing Spacemaker to play an important role in shaping the future that we want. I'm here now, so if you want to get in contact and hear more, just reach out, or you can contact us at spacemaker.ai. Thank you for listening. Of course.
Where have you actually used this, and have you got any great examples of clients and what you've done with them?
Yes, that's a good question. One of the largest construction companies in the world is actually using this, and just finished a project where they're designing, I think it's around 600 apartments, and they were able, and they used it together with their architect, so they were able to discover more than 70 extra apartments, which is 30 million in value. But what's even more exciting is that they actually increased the living qualities of the overall project, and also on the worst apartments in the project.
Wow.
Yeah.
Well, that's very exciting. Thank you very much, Håvard.
Thank you.